In this lecture, we are going to understand how we can sort elements present in an array using the merge sort algorithm. Merge sort is a fundamental example of divide and conquer algorithm. And also, it's a very famous sorting algorithm. In merge sort, what we do, suppose we have an array, we divide it into two halves, we get two individual array, and we do the same to them. That is, we again divide them in halves and we keep on doing that. So when we are going to stop? We will do it till further division of array can no longer take place. And this happens when you reach single element arrays. So then we cannot divide it further. Let's see exactly how this happens. For the given array, we have a lower bound, which is the index from where the array starts. Obviously, it is 0. And we also have upper bound, which is the last index of the array. Here it is 6. Now to divide this array into two halves, we need a mid value, where we can partition this array. We can calculate this mid value by adding the lower bound and the upper bound, and then dividing the value by 2. This will give us an int value. In this example, it will be 0 plus 6 divided by 2, so we will get 3. So this is the mid index. So the first array will start from the lower bound to the mid index, and the second array starts from mid plus 1 to the upper bound. So for this example, the two arrays we get are one from 0 to 3 and the other one from mid plus 1, which is 4, to the upper bound, which is 6. So this is how we're gonna partition the array. But what if the upper bound is an odd number? Let's say if it is 7, then how we're gonna partition the array? If the upper bound is 7, then the mid index we will get will be 0 plus 7 divided by 2, which will be 3.5, right? So after rounding off, we will get 3. So the first array will start from 0 till 3, and the next array will start from 4 till 7. This is how we will partition the array. So here you can see these are the two calls we are making to partition this array. And after the partition, we are getting two arrays. Both are having their own lower and upper bounds. So further partitioning of these produced subarrays will be done by these recursive calls. We don't have to do it, we just partition them once for the first level. So this was the first step of the divide and conquer algorithm, where we divide the task. And this involves recursion to do that division till we reach a certain base case to stop that division or to stop that recursion. And the base case is when we only have a single element in each array, which is when the lower bound and the upper bound index becomes the same. So we divided the problem into subproblems, and then we did everything recursively for those smaller subproblems to get to the very base values. The smallest subproblems are just single elements, they are just constants. So we covered the divide step and the conquer step. Now the most important step of merge sort algorithm is the combine step, because it's having the core logic that how we actually gonna sort these elements. So when we are solving the divide and conquer algorithm for different problems, then sometimes the division into subtasks might require the core implementation, and some other time it may be the combine step that require the core implementation to solve the problem. And this you can see with this merge sort algorithm, where the combine step require the core implementation to solve the problem. And the divide and conquer step were really straightforward. So how this combine step is to be done? How we are going to combine all these arrays? If we are merging these two subarrays, then this must be an array having 9 and 17. So 9 will come first and then 17. And then if we are merging these two arrays, then the output will be an array having elements 5 and 33. Similarly, for these arrays, so we merged all the list having single elements to a list having two elements. Now, merging these lists having two elements into four elements will result to these lists or to these arrays. One having elements 5, 9, 17 and 33 and the other having elements 7, 11, 19 and 25. And this should be the result, and this is how this algorithm should work. So at this point here, let's understand how we can merge these arrays back into a list having all the elements in ascending order. Let's say the first array is named A and the other one is B. And this will be the merged array or our much awaited solution. We're having a pointer I at the first element of array A. We have a pointer j pointing at the first element of array B and a pointer k using which we're gonna fill up the elements at the correct index in the solution array. So let's start. The element at ith position in array A is 5 and the element at jth position in array B is 7. We're gonna compare both the elements and we will put the smaller one in the solution array. Fair enough? So now the kth position is filled. So let's increment the k and also increment I by 1 as we've already picked 5 from A. At this instant, j is still at 7 and I is on 9. Again we compare these two and find out that 7 is smaller one. So we pick it and place it at kth position in the solution array. Again we increment the k and this time we increment the j. Again check for the smaller one and proceed. So this is how we're gonna merge two arrays into a single sorted array. So I gonna go all the way up till the middle index m and j is going to go till the upper bound. And then check for the smaller one from A and B at its ith and jth index respectively. If the element at index I is smaller, then put it in the solution array and go ahead by incrementing the I. Else, put the element at jth index of array B into the solution array and increment the j. And after putting the element in the solution array, increment the k. So I hope you got it. But this solution is not complete yet. Think of the case when the length of these two arrays are not same. One might be smaller than the other one. For example, array A is only having 2 elements and B is having 4 elements. Then what? So we need to cover this case as well. If the pointer I reaches to the middle index or to its limit, then we just need to get the remaining elements of B just by incrementing the j. No comparison, we go straight. And same is true if j reaches to its limit and I is still stuck there with more elements next to it. So if any of these two conditions fails, then check if there are more indexes to be traversed by I. If yes, get all the elements one by one just by incrementing the I and k. And also do the same for j. Now the solution is complete. Now let's analyze the complexity of merge sort. Let's first talk about time complexity. So the operations we have are we keep dividing the array into two halves until we reach to the base case, and we keep merging these halves upwards to construct the complete array or to construct the complete list, right? So how many divide operations it's gonna take to reach to the base case? we are dividing the arrays in halves, right? At each step, we are dividing the arrays in halves. So this is gonna take log n time to reach the base case. For example, if you have 8 elements in the array, then it's gonna take log 8, that is 3 divide operations. After the third operation, you will be on the base case. So if you're having an array or a list of 8 elements, then it will create 2 halves having 4 each, and then it will create 4 arrays having 2 elements each, and then will create 8 arrays having 1 element each, right? And if you are having 16 elements, then number of operations will be log 16, that is 4 operations. You will start with 16, then you'll get arrays having 8 elements each, then 4, then 2, then 1. And here you can see that right after the 4th operation, you are at the base case. So dividing the array till the base case will have log n complexity. Now let's talk about the merge operation. At each level, we are having n number of elements to be merged. However, not all at once each time. Still, as a whole, at each level, it's gonna consume order of n time. If you see here, when you reach to this step, merging all the lists below, here you will be having 4 elements in the first list and 4 elements in the other list to be sorted and merged to generate the original list. So in this list, you have to go through 4 elements, which is actually n divided by 2, and the same is true with this other list. You have to go through 4 elements, that is n by 2. So total of n elements to make the result. Similarly, at all the other levels, you're doing the same. If I talk about the levels just before it, here we are doing the same. We are merging 4 lists of n by 4 length each to make up these 2 lists of n by 2 lengths, thus again making a total of n. So at each level we are doing the same. We are getting a total of n. That's why the complexity will be order of some constant multiplied by n. And after ignoring the constant factor, we will be having complexity, time complexity order of n for this merge operation. We can verify this using the recurrence relation. The recurrence relation for this will be 2t n divided by 2 plus on, which will result to on log n time. Here in this recurrence relation, we are having 2 recursive calls of n by 2 size, and we are having n as the complexity for merging the subarrays. So this will give us on log n. You can solve the recurrence relation using the substitution method explained in the recurrence relation section to verify this time complexity. Now let's talk about space. So we are creating 2 temporary arrays to store the numbers of original array in the first call, and then we follow that and we keep creating the arrays to store the elements. We are storing n number of elements at each level, right? So this will be having order of n space.